Okay, I forgot to come back and put these. I've added 4 problems, but to your homework. But the nice thing is, and I wanted to go over polarization because it's such a huge physical phenomenon, and some of you will have to deal with it, and it's just one of those things that should be should have some exposure to it before you leave a physics class, and so. Uh, what I've done is you've got this assignment 14 now, homework number 14, and it's only, well, it's unavailable to students right now because it doesn't become available until like noon. All right, so, but anyway, or at 11:59 a.m. But anyway, it's only 4 problems, and um, here's how it looks. You edit the assignment, organize organize content. I'll show you what it looks like real quick. Um, Look, I'm giving you get the assignment's only worth 10 points, but it's still a homework assignment, so it still counts. But you'll get all these extra credit points, which will kind of boost your homework. Might boost your overall homework score if you do this by about 0.5%. It's kind of my little mea culpa for saying, "Oh, sorry about that." Anyway, so I wanted to talk about polarization real quick. This will be like a little 6 or 7 minute lecture on polarization, and then I will look at 2 of these problems today and maybe 2 of them tomorrow. All right, out here. Oh, not out here. Let's go to the slides. Okay, so here's polarization. All right, light's coming at. I think we talked about this. Okay, now this is the light coming at you. Now light, we're getting a sideways view. So remember, the vector is coming towards us here. This tells us that it's going in both directions. So we've got polarized light going in all directions everywhere. This is unpolarized. Now when it's polarized, um, it's partially polarized here. So what we're saying is some of the X components have been knocked out of this one. God, and then when we linearly polarize the light, not fully polarized, but linearly polarize the light, only the y-axis stuff gets through. And so therefore since we've cut out all the x-axis components of the electromagnetic wave, we're only getting the y-axis coming through. So unpolarized light, the electric fields have random directions, and partially polarized light, the electric fields are clustered around a preferred orientation, and fully polarized light, the electric fields are all in the same direction. Okay? So some crystals absorb light at a particular orientation. It's just, and again, it's one of those things that was discovered by experiment. And I think we talked about this in class. I just didn't assign any homework problems for it. All right, and we will do a problem here on Malou's law. So you got a light source coming in, hits the polarizer. Now these are 2 things of the same material. Half has already been knocked out, but look, this one's still oriented the same way. So it's a strange thing because you might be thinking, well, would another half? No, because it's able to get through there the way it's oriented. So they just keep marching on through. Okay. It's kind of like if you're walking along, twirling a long rod that's not quite as long as you are, tall as you are, but you're twirling a long rod. You're walking through here, and then you go through a narrow doorway. Bang! It knocks the rod out of your hand, and so all you can do is keep walking. Come through another doorway. You can still keep walking, but you don't have the rod anymore. All right? Now, here's what happens. You come walk along, twirling your baton, your rod. Bang! All right? Knocks the rod out of your hand, only the y-axis. Now you come to a door that's now like 6 inches high and a wide slit. Bam! You hit that. You're not going through. All right? And the equation for handling that is equal to I naught times cosine squared of theta. All right? Now here's a 3-banger. I don't think I'd do a 3-banger to you, so we just do 1 or 2, and you might have to do one of these on the exam. All right? So what this becomes, so here is where we really focus. So we've got I naught over 2, and then it becomes I naught over 2 cosine squared of theta of this last angle here of the second polarizer, which we call the analyzer. Well, then the last one's the analyzer. All right, but in this case, they're putting 3 up here. The transmitted, as it goes down, is that's known as Maloo's law. Now, here's a cool thing. Light is partially pulled upon reflection and refraction. For a particular angle called Brewster's angle, the reflected light is completely polarized. All right, so here we go, boom. So here's partially polarized light that might hit our eyes off water. But if you get it right at the right angle, we've got this linear polarized light coming towards us. All right, and so here's one. So here comes linearly polarized light. It was pretty intense, and then it comes out linearly polarized. And so that's when you see those dark spots out in the water. And then if you put on sunglasses, boom, it cuts out the glare completely, and you don't see the dark spots anymore. Of course, everything's a little bit darker. And Brewster's angle is N2 over N1. Okay? So it's going from, so in this case, N2 is if it was water over air, so N2 over N1, it's the inverse, the actual angle. We can prove it. I think I proved it in class, but I'm not sure. No, I didn't. But anyway, it works out using Snell's law. You can use some trig functions and come up with Snell's law, but I'm not going to do that. Just know that Brewster's angle for the angle of polarization is equal to N2 over N1. Right? And yeah, and unlike the critical angle, which can get you into, because Brewster's angle and the critical angle can get you in trouble because the critical angle is the sine of theta of N2 over N1, and N2 has to be less than N1. Not so the case here. 1.33 for the water, 1.01, because the tangent can be greater than 1. Okay? Just wanted to let you know about that. And then there's different materials that behave in a certain way with polarization. These are optically active materials, are able to rotate the plane of polarization of light being transmitted. And light scattered from the atmosphere is partially polarized. And some animals, because of the scattering in the atmosphere, you get this partially polarized light. Here's linear polarized light. Some animals appear to be able to detect this polarization and use it for navigation. That's what they're thinking with honeybees and things like that, or monarch butterflies, birds, certain birds. Cool stuff. And this scattering in the atmosphere has an intensity, and I think we talked about red sky at morning. This means that shorter wavelengths dominate the scattered light. This accounts for the blue color. Scattered light in the atmosphere has an intensity that is inversely proportional to the fourth power of the wavelength. Okay, whatever. This means that shorter wavelengths dominate the color. In other words, red wavelengths are longer, so they get knocked back. They scatter back, and we don't see them. Whereas the shorter wavelengths get through. They scatter through, so blue gets through. The scattering along the scattering off dust particles also yields the red colors of sunset. Okay, so red sky at morning, sailors take warning. All right, because in fair conditions, you've got a lot more dust than in stormy, rainy conditions. All right, in fair conditions, so when you're looking to the east, that means that the fair conditions are already by you. And then when you're looking to the west at night, red sky at night, sailor's delight. Oh, when you're looking to the west, that means the fair conditions are coming towards you. If it's a red sky in the morning, that means the fair conditions have left and that you can expect some stormy weather coming, a low pressure center. All right, so there we go. Just wanted to review the polarization, then we'll look at 2 of the slides. So we are at here. Let me get to this so I can turn this off.